Hello guys, welcome to the channel. In this particular video, I will explain the problem find the closest element in BST. So this problem is really interesting and asked by companies like Amazon. So let's see the problem statement. Okay, so here is the problem. It says that you are given a BST and an integer. You have to find the least absolute difference between any node value of BST and the given integer. So let me explain with this example. Here we are given an integer 13 and this particular tree, and we have to find the least absolute difference, right? So first of all, let me write the difference of like the absolute difference of this number from every node. So the first node that we have is 10, so 13 minus 10 will be 3. This is the first difference that we have. After this we have 2, so 13 minus 2 will be 11, right? And after this we have 11, so 13 minus 11 will be, what is 13 minus 11? It's simply 2, right? And we have 1 and 5, so 13 minus 1 is 12 and 13 minus 5 is 8. After this we have 3 and 6, so 13 minus 3 is 10 and 13 minus 6 is like 7, right? After this we have one node which is 4, so 13 minus 4 is 9. So these are the difference values that we have, and out of these values we have to return the minimum value. So minimum value is 2 here, so 2 is going to be the output, right? So I hope you have understood the problem statement. Let's talk about the solution now. Okay, so here I am going to write the same example that I have explained you. So the example is we have 10, then 2, 11, then 1, 5, 3, 6 and 4, right? So I'll write 10, then 2, 11, then 1, then 5. After this I have 3, 6 and 4. So I have 3, then 6 and then 4, right? This is the tree that is given to us, and the value of k is, value of k, let me write it here. So value of k is 13, right? Okay, so the first approach that will come to your mind is very similar to the one I have explained you. It says that you can traverse every node, and after traversing the node you can find the absolute difference and keep track of the minimum difference, right? So how to do this? This is quite simple. First of all, we have to think of the ways to traverse a binary tree. So what are the ways to traverse a tree? Traverse a binary tree, right? We have four ways to traverse a tree. First is level order traversal. The second is in order traversal. The third is pre-order traversal, and the fourth is like post-order traversal, right? So these are the traversal techniques that we have. We can use any of them. So let me move with the pre-order traversal. So how to write the pre-order traversal of a binary tree? Let me first of all let me copy this tree first. So I'm going to copy this whole example. Just copy this and paste it over here. So this is the example that we have, and now what I'll do is, okay, so first of all let me select this and place it over here. Okay, now we have to write the pre-order traversal. So in the pre-order traversal we have a function, let's say solve, and this function will have root as a parameter and this value k, right? So what we generally do in pre-order traversal is, first of all, this is a recursive function. So I will have if my root is equal to null. In that case, I have to return simply. And if the root value is not null, then we print root. We print root data. This is how we do the pre-order traversal, right? After this, we again call the function for left and right. Solve for root dot left, comma k, and root dot right, comma k. Okay, so this is a pseudocode. Now instead of printing here, you can see that at this point in the pre-order traversal I will have every node, right? And I'm printing that node. But in the question we don't have to print the node. All we need to do is we need to find the absolute difference. So let me just erase this. I'm going to erase this whole thing, and in place of this I'm going to write my absolute difference will be absolute of like k minus root data. This is how I can get the absolute difference, right? And after this I have to minimize this absolute difference. So I will have a data structure here to store the minimum absolute difference. So let's say this is a result and this is a list. This is a list. Now we have to call by reference if you want the change at this value, right? But if this is a global variable, then there is no value to there is no there is no need to call by reference. So I'll write my result of 0. The size of this is going to be 1, and after this my result of 0 will be minimum of result of 0 and the absolute difference that I have. This way, when this function completes, then I will have my absolute difference. So all I need to do is just need to call this function. So I'll call solve for root and k. When I call this function, then I will have my answer in this like this particular data structure. So I need to return result of 0. This is how we can solve the problem, right? And this is going to work fine. But I want you to notice one thing here. This is the approach that we need to follow in order to solve this problem. What is the time complexity of this approach? You can see here that I'm passing through every node using the pre-order traversal. First of all, I'll go to this, then this one, this one, this one, like so on, right? So this way the time complexity will be O of n, right? But we can reduce this time complexity. This is not the optimal approach. We can make a we can be benefited from this thing. We are given BST, not a binary tree, right? So how this is going to help us? Let's see. What are the properties of a BST? Whenever we have a BST, so let's say this is root node, root. So all the values in the left subtree will be smaller than root, right? And all the values in the right subtree will be greater than root. This is something which is going to help us a lot. How? Let me show you. So if I take the previous example, like this example, so for this example we are given 13, right? We are given 13 as the value. So if I check, if I compare these two values, this is the root value and this is the value k, right? So you can see that this value is greater. So if I go to these values, if I go to left side of the tree, then this is going to increase the difference. Let me show you how. 13 minus 10 is what? 13 minus 10 is 3. And all these value I know are smaller than this 10. Why? Because we are given BST. So if these values are smaller than 13 minus x, if this x reduces, then this difference is going to increase, right? So this way there is no sense of moving to the left if 13 is greater. So I can generalize this. I can write one thing, that if my k is greater than root data, in that case I will only move to right? And if I move to right, so you can see that I'll simply do 13 minus 11, and this way I will get like 2 as my answer, right? So for 13 minus x, you can see that if I try to increase the value of x, in that case I will get the minimum difference, and this is what I want, right? So you can think of the solution this way. Now all I need to do is, if my k is greater than root data, in that case I can simply move to root dot right, comma k, and I will have my function solve, right? So this is when my k is greater than root data. And else, if k is smaller or equal to, in that case I need to move to, okay, so let me remove this. I need to move to left side, right? This is what I can do. So now all I need to do is I just need to put the condition over here. So if I do so, then you can see that I will have my, if my k is greater than root data. Okay, so I can't write this one. I have to write if my k is smaller than equal to root data, and here I'll write else if my k is like greater than root data, right? So now you can see that in one in one function call, I will either go to this call or go to this call. You can see that. Why? Because there is a if else condition. So I will not call both of these function in at the same time. So this is going to reduce the complexity. So at first I will it may possible that from this I'll go to this side. I'm just talking about the possibility here. I'm not talking about what actually will be happen. So I can go to here, I can go to here, I can go to here, I can go to here. So this is the worst case, right? And this way I will be end up coming at this point. So this is the height of the tree. So this way the time complexity of this approach will reduce. So now the new time complexity will be O of height of the tree. So this is how we can approach this problem. I hope you guys will like the explanation. Now let me show you the code. So here is the code. On the left hand side I have the Java code, and on the right hand side I have the C++ code and the Python code. So in order to understand the solution, you guys just need to be aware of the pre-order traversal of a binary tree, and eventually you will be able to solve this problem, right? So this is all about this video. If you guys like the explanation, then you can hit the like button. Thank you.